The 6 big O classes. The complexities you'll meet in real code. There are infinitely many possible big O expressions in principle, but in practice, almost every algorithm you'll write or read falls into one of 6 classes. Learn these 6 and you can read any function's complexity. Data structures and algorithms foundations. 6 big O classes. A quick look back. Previously, we covered big O, the language of growth. We learned the 2 simplification rules: drop the constants, drop the lower terms. Any polynomial that comes out of frequency counting can be reduced to a clean big O expression with those 2 rules. We also met one class, O of 1. Constant time, the same number of operations no matter how big the input. We saw array indexing, dictionary lookup, stack push, and pop, all O of 1. And we covered the amortization caveat for dynamic arrays. Today, the 5 remaining classes. The ones that show up in real code, from the very efficient logarithmic class all the way up to the dangerous exponential class. Each one with a clear example you'll recognize. First, A of log n. Logarithmic time, the defining property, each step throws away half of what's left to look at. Not a fraction, specifically half or roughly half. The magic of logarithmic time, if you double the input, you only do one more step, not double the steps. One more, that's how a logarithm works. Logarithms grow incredibly slowly. So slowly that for most purposes, O of log n is almost as good as constant time. The classic example of logarithmic time is binary search. Let's walk through it. Find the number 42 in a sorted array of 1024 numbers. Without binary search, the worst case is to scan all 1024. With binary search, we'll be done in 10 steps. Let me show you why. Step 1. Look at the middle element of the array, element 512, compared to 42. The middle element is too low. Since the array is sorted, 42 has to be in the right half. We've just eliminated 512 elements in one comparison. 512 elements remain. Step 2, look at the middle of that remaining half, element 768, compared to 42. Too high, so 42 is in the left half of the right half. 256 elements remain. Steps 3 through 9, same idea, keep halving. After step 3, 128 elements remain. After step 4, 64, then 32, then 16, then 8, then 4, then 2. Step 10, we're down to a single element. Either that element is 42, found, or it isn't, in which case 42 isn't in the array. Either way, we have our answer in 10 steps, not 1024. The math, log base 2 of 1024 equals exactly 10. That's where the 10 comes from. Each step halves the remaining range, and the number of times you can have 1024 down to 1 is exactly log base 2 of 1024. Big O takes the leading term, drops the constants, O of a log n. And here's a callback worth remembering. Remember Euclid's GCD from when we defined an algorithm? 2,500 years old. Euclid's algorithm is also O of log n for the same reason. Each step of Euclid roughly halves the inputs. Whenever you see halving, suspect a logarithm. Why is log n so cheap? Doubling the input adds only one more step. Let me make that concrete with a table. At n equal 1000, about 10 steps. Log base 2 of 1000 is just under 10. 10 comparisons to search a list of 1000. Fast. At n equal 1 million, about 20 steps. Notice, we multiplied the input by 1000, but only doubled the work. From 10 steps to 20, that's the logarithm doing its job. At n equal 1 billion, about 30 steps. We multiplied the input by 1 billion compared to the first row. Only tripled the work from 10 to 30. 1 billion items. 30 steps, that's the magic of halving. When you can build an algorithm that throws away half the work at every step, you've earned one of the most efficient classes in computer science. Next, O of n. Linear time, the defining property. Visit each item once. Look at every element. Do the same amount of work for each one. Total work is proportional to n. The intuition, double the input, the work doubles. Triple the input, the work triples. Linear and predictable. There's no magic, no halving, no shortcut. just a single pass over the data. What does O of n look like in actual code? 3 examples, the kinds of operations you'll write every day. First, sum of r, the built-in function that adds up every element. It iterates once over the array, and adds total work proportional to n, O of n. Second, for line and file, a common pattern for processing log files, configuration files, anything line-based. We read each line once, doubling the file size doubles the time. Linear. Third, max of r, min of r. To find the maximum, we make a single pass tracking the running winner. Same for minimum. One pass, one comparison per element. Linear. The pattern, anytime you see a single loop over the input with constant work inside the loop body, suspect O of n. It's by far the most common complexity class in real code. Class 4, O of n log n. Quasi-linear time, a little worse than linear, but not much. This is the price of sorting. Every general-purpose sorting algorithm, merge sort, quick sort, heap sort, tim sort, hits this complexity. There's a beautiful theoretical result here. You cannot sort a list of arbitrary items faster than O of n log n using comparisons. This is a proven lower bound, not just a limit of today's algorithms. There's one caveat. If you know something special about your data, like that it's all integers in a known range, you can use non-comparison sorts like radix sort or counting sort that beat n log n. But for general data, when all you can do is compare 2 items at a time, n log n is the floor. So when you see n log n in code, you're often seeing a sort or an algorithm that uses sort internally. Let's walk through where n log n comes from. Merge sort 8 numbers by splitting in half recursively, then merging the sorted halves back together. The algorithm has 2 phases, divide and merge. Start with 8 numbers. The divide phase splits them into 2 halves of 4. That's level 1 of the recursion. Split each half again. Now we have 4 pairs of 2. That's level 2 of the recursion. We keep splitting until each group has just 1 item. Total levels of splitting equals log base 2 of n. Now the merge phase begins. Start with the pairs of 2. Merge each pair into a sorted group of 4. Each merge does some constant work per element. Across all the merges at this level, we touch n elements total. That's some work at this level. Merge again. Now we have sorted groups of 4 becoming sorted groups of 8. Again, n work across all the merges at this level. Final merge, the 2 sorted halves combine into one sorted array of 8. Another pass of n work. Add it up, log base 2 of n levels of merging. N work per level, multiply, n times log n. That's O of n log n. The pattern shows up everywhere divide and conquer is used. Class 5, O of n squared. Quadratic time, the defining feature, compare every pair. For each element, do work that depends on every other element. N times n equals n squared. The shape that signals quadratic, whenever you see a loop inside a loop, both running over the same input, that's almost certainly O of n squared. 2 nested loops, each iterating in times. The body runs in times and equals n squared times. This is the most common scaling problem in production code because it's easy to write without noticing. Let's see the numbers in concrete terms. Here's a textbook quadratic loop. For I in items, for j in items, compare I and j. 2 nested loops, both over the array. At n equal 5, 5 times 5 is 25 operations. Trivial, your machine does that in microseconds. At n equal 1000, 1000 times 1000 is 1 million operations. Still fast on a modern machine, a few milliseconds. At n equal 1 million, 1 million times 1 million is 1 trillion operations. Infeasible, your function would take hours, possibly days. It will never complete in any reasonable time. Notice the scaling. We multiplied the input by 1000. The work multiplied by 1 million. That's the quadratic penalty. Linear scaling versus quadratic is the difference between a service that handles 1 million users and a service that falls over at 10,000. The last class, O of 2 to the n. Exponential time, the defining property, at each step the work doubles. This is the most aggressive growth you'll see in everyday algorithms. you typically encounter exponential time with recursion that branches into two. Every call spawns two more recursive calls. You see it in naive solutions to certain combinatorial problems. The good news, exponential, is usually a sign that there's a smarter algorithm available. Finding it is the engineering work. The classic example of exponential time is the naive recursive Fibonacci. Compute the nth Fibonacci number by recursing into n-1 and n-2. Looks elegant, the complexity tells a different story. Each call spawns two more calls. Each of those spawns two more. The recursion tree branches and branches. The total number of calls is approximately 2 to the n. Let's see what that means in practice. Fib of 10, about 177 function calls. Your machine handles this instantly. No problem. Fib of 40, about 1 billion function calls. Now we're talking several seconds, possibly minutes, depending on the machine. The recursion tree has exploded. Fib of 50, about 1 trillion function calls. Hours of CPU time. From input 40 to input 50, the work went up 1,000 times. That's exponential, the good news. Memoization, or an iterative bottom-up approach, makes Fibonacci of n. We'll see that pattern later in the series. I want to drive home just how dramatic the gap is between polynomial and exponential. Even quadratic, which we already called bad, is in a completely different universe from exponential. Let me put numbers to it. O of n squared at n equal 1 million is 10 to the 12 operations. 1 trillion, that's minutes on a modern machine. Bad but possible. You could wait. O of 2 to the n at n equal 50 is 10 to the 15 operations. 1 quadrillion, that's hours of computation. You probably wouldn't wait. O of 2 to the n at n equal 100 is 10 to the 30 operations. That number is so large, no computer could finish it in any practical amount of time. Even the fastest supercomputers in the world together cannot make a dent in 10 to the 30 operations. Even at small n, exponential time is enormous. It's not a bit slower than quadratic. The algorithm takes longer than is practical. The number of inputs you can realistically handle is essentially fixed. Beyond a few dozen, the program takes more time than anyone can wait. When you see exponential time in your code, that's a serious problem. The growth curves, all 6 classes on the same chart. The x-axis is the input size n. The y-axis is the work done. O of 1 stays perfectly flat at the bottom. O of log n grows so slowly, it's almost flat too. O of n is a straight line, growing linearly. O of n log n curves up gently, sortable scale. O of n squared bends sharply upward. You can see the trouble coming. And O of 2 to the n shoots straight up to infinity within just a tiny range of n. The classes you want stay flat. The ones you fear shoot up fast. When you choose an algorithm, you're choosing which curve your function will trace as users and data grow. That choice is one of the most consequential things you do as an engineer. At a glance, what each class costs in operations. Here are all 6 classes at 4 input sizes: 10, 1000, 1 million, and 1 billion. Let's walk through each row. O of 1 is always one operation. Doesn't matter if the input is 10 or a billion. 1, that's the gold standard. O of a log n. At n equal 10, 3 operations. At 1000, 10. At 1 million, 20. At 1 billion, 30. Barely grows. This is why binary search and hash lookups feel instant even on massive data. O of n grows with the input. 10, then 1000, then 1 million, then 1 billion. Each row is 1,000 times the previous. Predictable, manageable. O of n log n. About 30, then 10,000, then 20 million, then 30 billion. A bit worse than linear, but on the same order of magnitude. The sorting penalty. O of n squared. 100, then 1 million, then 1 trillion. At a billion items, it's mathematically defined, but practically infeasible. No machine completes that in reasonable time. O of 2 to the n. 1,000 operations at n equal 10. Past that, infeasible at every scale. The class to avoid in production. Here's where we are in the series. Previously at Big O. The language, 2 rules: drop constants, drop lower terms. Our first class O of 1. This video, the 6 classes you'll see in real code. from O of 1 all the way up to O of 2 to the n, each with a walked example. Coming up, how to read big O straight from code. We've seen the classes. Next, we'll see how to spot which class a piece of code belongs to in a few seconds by recognizing patterns line by line. Beware of bugs in the above code. I have only proved it correct, not tried it, Donald Knuth. The line is funny because Knuth means it. Correctness gives you the right answer. Your code has to produce what you expect. Complexity tells you how quickly you'll get it on real input. Both matter, Knuth knew it. Thanks for watching. If this video helped you finally see the 6 big O classes clearly, please like, subscribe, and leave a comment below. Tell me which class you've debugged most often in production, or which one surprised you most. More on reading complexity directly from code is coming in future episodes in this playlist. See you there.